From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders of the 3D printing industry.
Focus on. So we have two approaches in terms of how we want to understand this type of printing. One is ex situ, so after the part's already been printed on a traditional printer. And then the other aspect is doing the measurements in the actual printing environment. So in resin, swollen, as it's printing, as it's polymerizing, the entire, like the whole kit and caboodle. So that in situ measurement is inherently, small scale, defined by that the region that you're polymerizing. But the important information that you can get from that is the length scales at which you're actually creating this polymer. So
that was Callie Higgins. Callie is a scientist at the National Institute of Science and Technology, where she focuses on photopolymer additive manufacturing. Her work focuses on using atomic force microscopy to detect and remedy flaws in additive manufactured parts. This research was highlighted earlier in the year when Callie was awarded the Service to America Medal for an emerging leader. Callie is a doctor of philosophy focused in optics and optical sciences and material sciences from the University of Colorado Boulder, and recently took a position as an adjunct professor at the Colorado School of Mines. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher.
Awesome. Well, I'm really excited for the conversation today. Callie, thanks so much for joining. We get started like all our podcasts. I'd like to put some context around everyone who I talk to and kind of get their full story. So where were you born? Where did you grow up? And kind of what got you down the kind of technical engineering kind of additive track?
that's awesome. So I was actually born in San Diego, California, and didn't actually grow up there. I grew up in a small town in northern Idaho, actually, right next to the Canada border. It's a lot like Colorado where I live now, but it had big bodies of water, big lakes, and a ski resort too. So it was an awesome place to grow up. I loved it. It was a small town, and so it really gave me a lot of opportunity to have more interaction with my teachers. And I come from a family of very powerful women. So I'm the youngest of four girls, and my sisters are all bosses. My mom is an animal. She's such an incredible woman. And so it made it very easy to only see like these amazing women succeeding. And so I never really thought that I couldn't be successful as a woman in the sciences. And so I naturally, whatever I, felt most natural kind of falling into in high school, which was physics, I ended up like falling in love with it and never really looked back. And then I decided to go to undergrad back in San Diego because I loved it so much. And I pursued physics. And so I got my undergraduate degree in physics with a minor in math, and really wanted to affect change and help kind of bring other young scientists out. And so I thought, okay, well, let me go to graduate school so I can become a professor. And so I applied to a bunch of different graduate school programs and ended up getting an awesome offer at University of Colorado Boulder. And it was for an optics specialty in actually electrical engineering. So it was interesting. I'm like the only electrical engineering PhD that has never taken a circuits class. And I fell in love with the way that light interacted with different materials. And so that's really what came about with this additive manufacturing, because we were using light to manipulate these different materials called photopolymers. So you shine light on it, it takes the material from liquid to solid, and that's how you build up your three-dimensional structure. And it's over the years that I've been so intimately familiar with it, it's just has really carved out a place in my heart in recognizing how important and impactful this technology, along with all additive technologies, can really have broadly across society.
That's awesome. And so what was the first time, what was your first experience with additive manufacturing? Was it kind of from the laser side, or had you seen it in other contexts?
I'd seen it kind of in passing as this like Tinker toy, like I'd seen like the Maker bots. Mm-hmm. But I think my first direct experience with it was actually using additive manufacturing and using a Stratasys printer to print a component for a printer that I was building.
Right.
So I was trying to build, because obviously optics is my background. And so I was building an optical system for it was specifically a digital light processing, like DLP based vat photopolymer system. And so I was building out that system so it could be really modular for my research. But I needed some components that I just couldn't go machine. And so I just decided, okay, well, I'll just build up the CAD file and go print it.
Awesome. So when did you get into NIST, or when did you kind of get that opportunity?
Yeah, that's a great question. So as I mentioned, I really wanted to go to graduate school because I wanted to be a professor, because I wanted to teach. I was just so excited. But then throughout graduate school, as some of us, I think, experience, I just kind of saw the lives of the professors around me. And it was an R1 like university, so very high level of research. And I just essentially saw that they had 3 full-time jobs that very few could manage to do successfully, or without being miserable, you know. And so I didn't think I wanted to pursue that. In addition, like, I mean, to be honest, like I was done with research. I was so over it. I was in a dark lab all by myself, pretty much doing a project by myself. And I need more interaction with people. Like, I think we, especially in this field, get so much benefit from the ideas of others, because that's what makes this so great, is like everybody has different ideas and different perspectives. And so all of a sudden this technology is like driving in this crazy new direction. And that's what helps create the technology itself. And I just was just kind of over it. But I had a couple of different industry jobs that I had offers to. But then my collaborators at NIST, I was collaborating with them at the end of my PhD to do some atomic force microscopy on these tissue engineering samples that I was fabricating, because we needed to have really small scale analysis of these materials, because we were engineering them to have different mechanical properties using that light patterning system. And we need to measure them. And there aren't very many tools that can do that. And atomic force microscopy is actually uniquely well suited for this. And so I was collaborating with them, and they asked me to write a proposal for, it's called a National Research Council, or NRC, postdoc. And it's a 2-year commitment if you end up getting the actual fellowship. And I was like, well, why not? Like, it's a 2-year gig. I've really enjoyed working with these 2 people. They are awesome. I like this environment. I would be able to stay in Boulder, Colorado, where obviously I was going to school and I wanted to stay. And I ended up fortunately getting, like, my proposal was funded, and I fell in love. It was just such a different environment, both from the perspective of all of a sudden no longer having this kind of like dichotomy in terms of like a hierarchy almost. And obviously your PhD, you're your advisor, you're the advisee, but all of a sudden I was just finally the accepted expert in my field. You know, I was a colleague as opposed to someone who was inferior, even to people that were 15 years senior at NIST. They saw me as a colleague, and that was just so refreshing and so different than the academic experience that I had, that I just couldn't believe that I could be able to do research in this setting. And I had access to incredible mentorship. Jason Kilgore, who's been the project leader for all of this work, he was, imperative to all of this work. And that's what really kind of got me locked into NIST. And what's interesting about NIST also that a lot of people don't know is that it is the only national lab that is directly funded by Congress. So we are a line item in their budget. So we can't write proposals. We're not allowed to, but we are directly funded from Congress. So we don't have to write proposals. So it allows us to kind of interestingly like pursue a little bit more risky research, because we're not funded by either companies or different, agencies. And this is really interesting because it allows us to interact with stakeholders and industry partners in a very different way. So we have no skin in the game. We have no incentive to help with the community other than for the altruistic reason that NIST exists, which is to help drive innovation in commerce across the United States. Like, that is literally like NIST's kind of broad mission statement. And it's just refreshing to be able to be in that position where, I want this field to succeed. I don't care about making a dime off of it. I just want the field to succeed. And that's just so unique to NIST that I've been really fortunate to be able to capitalize on.
And how big is, I mean, NIST, I mean, that's a big mission, right?
It is.
And
It's
so
huge.
like you can, and you can parse it in a lot of different ways, but like,
Right.
I guess how big is the manufacturing or even kind of the additive manufacturing piece of that? If you think of kind of the global or like even the US economy, right? Like additive is
Oh my gosh,
a
it's so
sliver,
small
right?
at NIST comparatively.
Yeah.
Right. Like it's, additive manufacturing at NIST is, I don't know, maybe like 1 to 5% of NIST maybe.
Okay.
And specifically photopolymer additive, which is the work that I do, is a small fraction of that. So metals additive is the most concerted effort, which is awesome because it's the most mature and has so much, already in existence in that space. And since I started at NIST, we've really started to focus and have a concerted effort in the photopolymer additive space, but it's growing. And that's what's really exciting, is to have the flexibility to actually grow the program and interact with industry in this way so that we can actually help drive the field forward.
And one thing that you mentioned before is, I'm going to put my material science hat on for a second because I hadn't heard the term in a long time. But so AFM, from what I remember, and I haven't used it in a long time, but it's kind of like you have a probe that is kind of going along a surface, and you kind of create a map, so to speak, but it's at like super small level, or like almost the molecular level, not that quite that small, but really small.
Exactly. That is exactly what it is. So I
would have passed that.
No, that's a great kind of synopsis. So the work that we do, what's interesting about atomic force microscopy is that it has evolved into this unbelievably flexible tool. Like you can get chemical spectroscopy on the system. You can get mechanical properties like viscoelasticity. So you can get how stiff a material it is, how damp the material it is. You can get topography, which is kind of the initial, invention of the material or of the characterization tool. But you can get magnetic properties, electrical properties, and it's all at the length scale of the tip or probe that you're using. And that's, on the order of nanometers. So you can, like IBM has demonstrated the ability to resolve atoms in these systems. So it's an unbelievably flexible tool to capture a lot of the relevant kinetics and mechanical and chemical properties in these types of systems.
So how does it work? I mean, I typically think of additive is you've got a bunch of layers that are just going to throw kind of your standard material model off, right? Because the process and how it's built makes so much of a difference. There's porosity, there's directionality. How does it resolve when, like, if you just look at a little piece of it, like you can get some data certainly, but then extrapolating that out, like how do you think about that? Or is there is that applicable when you can kind of get some localized measurements of the part or the material, but then extrapolating that to a process?
Yeah, that's actually a really great question. And that's absolutely one of the main things that we're kind of trying to focus on. So we have two approaches in terms of how we want to understand this type of printing. One is ex situ. So after the part's already been printed on a traditional printer. And then the other aspect is doing the measurements in the actual printing environment. So in resin, swollen, as it's printing, as it's polymerizing the entire, like the whole kit and caboodle. So that in situ measurement is inherently, small scale, defined by that, the region that you're polymerizing. But the important information that you can get from that is the length scales at which you're actually creating this polymer. So if you think that you're patterning a 2 micron line and you see that your material is actually diffusing 30 microns away from that, that's very, very, very important. And because that drives your resolution, that drives the minimum feature size, that drives how fast you can print. I mean, it affects the entire printing system. And so those are the kind of measurements that we're doing at NIST. And then on the other side, this ex situ side, we have one tool. When we use atomic force microscopy, it's destructive test, but we can essentially use a fancy meat slicer and cut off the top of the structure, or the through thickness of the structure, so that you can actually measure the mechanical and chemical properties in through thickness. So what we have is essentially an elastic modulus map of the layers of that print. So you can actually visually and now, for one of the first times, see the mechanical changes that occur that are inherent to the printing process itself. So this gradient of mechanical properties at every single layer. We know that exists, but now we actually have the experimental evidence of that as well. And that's at the right length scales for atomic. It's actually the perfect length scales for atomic force microscopy. And then we're also developing additional tools that aren't destructive, which are using X-ray CT to do, at least at this first go, doing fidelity calibration. So, hey, here's this CAD file that we designed. What did we end up printing? And how did the resolution of the structures affect the final print, like fidelity? If we try to print a really small structure, what ended up happening? If we printed a really big structure next to a really small structure, did we end up, reducing the fidelity of one feature versus the other? And which is actually what we're observing. And so those are the kinds of measurements that we're trying to develop at NIST.
So when you capture this information and this research and I presume publish it, is the goal also to get that into like a standard, or is it like a more repository of information? How does the output of work that you're doing and the results kind of get into, or like what happens to them?
Right. No, that's a really great question. Yeah, I know. National Institute of Standards and Technology. So it's definitely part of our name, the standards piece.
Yeah.
But initially, because this project really got off the ground when I started 4 years ago at NIST, we've been just really focused on developing these fundamental science metrology tools to help facilitate the growth in this field. Try to address the needs that are arising in the field as they happen. And so that's developing these like fundamental, like voxel level measurement technologies so we can understand the process and then extrapolate it forward. But then all of this informs, the interactions that we have with our stakeholders. So if industry is like, hey, like we really need a highly calibrated light source, like we need something that we can use and as a reference for all of our printing systems so that we're not, needing to reinvent the wheel every single time we do a print or every single time we build a new printer. And that would be something that we would, make sure that we tackle, And so we're very sensitive to the needs of industry and we want to evolve with those needs as well. So that's kind of how our results get out. So we, not only do we publish the work, but we're also actively involved in, as we have this photopolymer additive manufacturing alliance that was just formed by NIST and then this trade association called RadTech, and its focus is engaging the community broadly and then having it kind of feed back into the research that we're doing at NIST, and be it standards, be it new research, and that community would have ready access to the work that we are doing. So they would know, hey, we're coming out with this new metrology tool. Look at, like, here's the manuscript. Here's how it could be useful for your new system. And so that's kind of like what we're building our project out to be.
I think it's so cool to see the collaboration between industry and organizations like NIST and others to tackle some of these broader problems that occur in the industry, right? Like a company can't solve that problem on its own, right? And
have the capital to do it.
Right.
They don't have the capital. You can't see the return on that investment. Like doing fundamental metrology in your system isn't going to make you $1 million, but that foundation will enable billions of dollars of growth in the field. And so that's what we're trying to enable.
For sure. Yeah. I mean, we've even seen it. We're part of America Makes, and we actually sit on some of the common data dictionary and common data model working groups that are kind of led by some of your colleagues, Yan Liu and others on the NIST side. And so it's helpful for us to kind of be part of that conversation and hear kind of what a lot of people think about different topics. So it's really, really cool to see. And so kind of all along all of your work that you've done, you've recently kind of been awarded a pretty significant honor in the country, really. So do you want to talk a little bit about kind of your leadership award? Yeah.
So I was awarded the Service to America Medal for emerging leaders. And it's just, so this type of award it's one of 7 different awards that they give out every single year. So last year, Fauci got Federal Employee of the Year. This year, the 2 people that got Federal Employee of the Year are the people that invented the spike protein or the functioning piece of the coronavirus vaccine. So those are the kinds of people that share this space. And what I was so excited about receiving this award for was that it lent so much credibility to the fact that the United States recognizes that additive manufacturing is an important field and it's relevant enough to give someone an emerging leader award for. Like that's what really got me so excited, because the selection committee is comprised of what's supposed to be representative of the entire United States broadly. So it's congressmen, it's elected officials, and, among congressmen, it's, CEOs of companies, it's celebrities, it's really the whole swath of the United States. And to have them broadly recognize that additive manufacturing is important was just really encouraging and rewarding to see, because all of us believe it, but I think it's just a testament to how impactful the field is becoming.
And how do you see it kind of emerging in the next few years? I mean, there's different levels, right? Like on the production side, like technologies are getting into the actual final parts. Like there's more and more universities are incorporating it into kind of parts of the research, even like general kind of professor research directions, like most often, like a lot of the new stuff is in additive related fields. Like, what are you seeing from where you sit at NIST?
Yeah, so that's funny that you mentioned, academic institutes recognizing that, because I was just hired on for a faculty position at Colorado School of Mines, specifically to be a photopolymer additive scientist and researcher. And so, like, definitely universities are recognizing that. But I think that the biggest, or at least from the photopolymer additive perspective, I think one of the biggest impacts that this field will have is in regenerative medicine, because it is the only technology in existence that can engineer at the length scales that are relevant to create representative tissues for humans and other people. And so this has broad implications for, pharmaceutical development, reducing the need for a lot of different inaccurate animal models, though those are all we have. And so we have to use animal models for a lot of these systems. But I think that that's really going to be this giant revolution in the field. Once we can harness and really understand the chemical and mechanical properties of these structures, then we can engineer them to be exactly what a cell needs to differentiate and turn into, say, bone tissue or cartilage tissue in the exact three-dimensional geometry that's required for that tissue. And that's where I see the most dramatic, ready impact to society, at least from the photopolymer additive side, because that's really what I can speak most to right now.
So not engineered meat.
Oh, definitely engineered meat too. Absolutely. I think that's huge for climate change. I think that's unbelievable. That's totally in line with this regenerative medicine. That's exactly what it is. I have a friend that is working at a 3D printing company in San Francisco that did his PhD with me, and he's literally building out the scaffolding to engineer the muscle tissue to turn into something that's representative of meat. Like, that's beautiful. Like, how elegant of a solution is that? And to make it, obviously right now the hurdle is, cost and actually having it be functioning and representative. But I think those are a lot of hurdles that are becoming less and less daunting.
And so what, can you tell us more about the kind of role you'll have at Mines? Are you going to be teaching, or is it more of a research role?
Yeah, so I've actually, I didn't want to leave NIST because I love this unique third-party perspective and this unique kind of ability to kind of, play in this space while serving. I mean, I really enjoy the fact that I get to serve. I really still wanted to have this other piece of being able to interact with industry in a different capacity and with other academics, and have more ready connections and collaborations and access to, awesome young minds. And so I'm developing a joint appointment between the two. So I'm trying in this early stages, it's a programmatic level. So it would be focused on photopolymer additive between the two institutes. But then down more broadly in the next 5 to 10 years, my vision is to build out a center that encompasses more than just NIST and Mines, but the other major research universities and institutes in the Front Range, in addition to a lot of the companies that have been moving into Colorado. Yeah,
and I think I've been in the Colorado region, Denver region recently, and
awesome.
It's an amazing the amount of additive work going on there. I mean, I heard EOS just like they have at least 100 machines in the Denver area. And so the amount of stuff that's going on between mines and some of the industry partners is pretty crazy.
Mm-hmm. It's incredible. I mean, it just shows how impactful this field can be, and it is already. So it's definitely very encouraging.
So kind of switching gears a little bit. I mean, one of the goals of this podcast is to kind of not only share stories of successful practitioners of additive manufacturing as yourselves, but also kind of give helpful hints or kind of lessons learned to some of the folks that are learning about the field or kind of emerging or wanting to do a career change. So kind of taking from your career and kind of what you've done, of what sorts of advice or what sorts of skill sets, maybe more tangibly, do you see as being very beneficial in terms of the people you like to work with or people that you've been seeing that have been successful in the space?
Mm-hmm. That's also a really good question. I think, I'm a bit unique of a scientist at NIST just because I've really focused a lot on the stakeholder engagement piece in addition to my technical expertise. But I think what's made me successful is that ability to communicate the science that I'm doing and the relevance of the science that I'm doing. So understanding not only the fundamentals of what you're doing, but also being able to talk to, either your superiors or to other stakeholders or other people in this space about what you're doing at a level that not only can they understand, but they can appreciate. So I think that communication is a really huge portion. Also, like providing context and education is really important because a lot of people don't know at all what we do or what it even involves or why it could be incredibly useful. And so I think educating people in terms of what is possible with this type of technology is really important too. And then other skills that I would say are just, a very strong passion for the field. Like I know that you can't magic that out of thin air, but if you're in the field or you're transitioning into the field, you're already going to be passionate about this. And so that is inherently something that allows you to kind of push beyond the bounds of what other people might be doing if it's just like their day job or something. Like I've been successful because I am very excited and see a lot of the value in the direct work that my group is able to do. And so it becomes very rewarding. And I think when you feel rewarded, you're more likely to put a lot more work and effort into something. And I think that's ultimately what leads to a lot of success. And then I'm trying to think, I mean, obviously, you want to have the technical expertise, but I really do kind of just to go back to it. I really think that the communication portion is just so important. That's why it's so nice to have these kinds of podcasts. Like this podcast is so helpful for people, to get a flavor of these different types of positions, different types of printing, different types of jobs. And this is a communication mechanism. This is a way for people to learn. And I think there's so much value in that. So I really appreciate this opportunity, definitely.
Yeah, and one of my kind of ideas that I've been kind of just thinking about over the last few years as we've kind of done the podcast is that it used to be in the US, certainly 20, 30 years ago, you might have someone in your family that was in manufacturing, right? Like because the whole industry for a lot of regions in the country have been hollowed out. It's not always the case that anyone that builds anything or goes to a manufacturing plant or works on one of these nondescript windowless buildings on the side of a highway. And so the ability to know what it is when you say I work in manufacturing, like it's lost on many people just because it's kind of gotten out of the day-to-day lives of many, many areas. And so it's, I've always thought it's really interesting to kind of shine a light on some of these things because like you can't just walk into NIST, right? Like and see all the cool stuff that you're doing, right? And same with most manufacturing places is like you just can't kind of go in and see and like if I wanted to be a baseball player when I was growing up, so I can see someone on TV being a baseball player, but like it's a little bit different. So.
Right. I know. So that's like one big part of the role that I'm trying to play also is a lot of, outreach, going and talking to middle school kids, going and talking to high school kids, like showing them what a scientist can look like and what my job can be, what your job can be. Like, hey, you can get your education paid for if you want to, like all of a sudden that opens up a lot of doors. So I think exposing people to the options is so helpful.
And so you've got a lot of kind of irons in the fire in terms of kind of your next appointment. But I guess from a research standpoint, you've highlighted a little bit on kind of the tissue engineering piece, but kind of on the metrology piece, like what's really exciting about, or like, what are you excited about kind of taking to the next level with your research and the work you're doing in additive?
So one very specific aspect that we've, just to kind of highlight, I think it's nice to provide some examples, is that we are developing a metrological light engine or metrological 3D printer. So something that's a very well characterized and well calibrated entire modular 3D printer. So something that has, a very, like, the most uniform projection plane, for instance. So we were designing specifically a DLP based system just at this standpoint, but really characterizing every single voxel of that entire projection. Like that's exactly what we think that we've been informed by the field that's needed. And then building that into an existing 3D printer such that it can be a bit modular, so we can incorporate different characterization technologies. And I think that's one really big direction.
Awesome. And so one kind of broader question as we kind of get to the tail end of the interview for today, but like if companies or individuals are interested in kind of working with NIST or kind of finding out more of like what the cool work you're doing or others in the group are doing as it pertains to additive or just broader sense, like how do they go about doing that? Is it like, do they find a kind of a working group that you're doing? Just go online? Like how do most companies start to get involved?
That's a great question. So most companies have gotten involved because I've directly really started contacting people. Like I've been really boots on the ground with that. But it has since grown into this, as I mentioned, Photopolymer Additive Manufacturing Alliance. And now that's a new, more efficient conduit for companies to interact, because it's a landing spot aside from the NIST landing project page that we have that really allows people to see what's happened. And then it has all of our webinars, all of our workshops that we've had with reports on the field that is just a really nice access point. So I would say that's probably the most efficient way to really see broadly what's happening in the field. But if you're interested specifically to NIST, I would say our page, our Photopolymer Additive Manufacturing Project page is a really nice resource, because it has all of our manuscripts and then high level description of our work, and then all of the people that are scientists on this work as well. And it really has a nice connection to this PAMA alliance, and then also these other workshops that we've hosted at NIST. So that would be two main mechanisms to see the work that we're doing. And I'm always happy to talk with people, so they can definitely email me directly if they want.
That's awesome. So we'll put all that info on the podcast page when we post it. And I want to thank you so much for joining the episode today. I feel like we could kind of do this again in 6 months, and there'll be like a ton more to talk about with all the work that you're doing and activity that's going on at NIST. So I really appreciate you taking the time today to chat, and good luck with all the future endeavors that you're up to.
Oh, thank you so much. It's been such a joy. I really appreciate the work that you're doing here. This is awesome.